Welcome back to the Iron Range Engineering Dynamics course. We are in the Foundations section of the course. This is video number 6. We're doing sample problems, and this is a kinetics sample problem of the type conservation of energy. In this problem, a 50 kilogram box is resting on an inclined plane of angle 35 degrees. It is compressing a spring with a K of 100 pounds per foot by 2 meters. When the spring is released, the box travels up the incline 25 feet before stopping. Find the coefficient of kinetic friction. Better change that word to up. So step 1, let's turn these words, this paragraph, into a picture. So we've got an inclined plane. Angle 35 degrees with a spring and a box. And this spring is compressed 2 meters from its natural state. So if I took the box away, the spring would extend out another 2 meters up the incline. Let's call this point of the box point 1. It then travels, the box travels up the incline a distance to point 2 of 25 meters. Oops, 25 feet. The mass of the box is 50 kilograms. The coefficient of the spring coefficient, or the spring constant, from Hooke's law is 100 pounds per foot. And there is friction between the box and the incline, and there will be some coefficient of friction, and we don't know what that coefficient of friction is. So a few more pieces of given information here. The distance traveled is 25 feet. The angle of the incline is 35 degrees. And the compression of the spring, let's use X for spring compression, is 2 meters. And we are asked to find the coefficient of kinetic friction. So from an energy perspective, let's see what's happening here. When the box is at its original position, it has this spring compressed, so it has a whole bunch of potential energy. And then as the box travels up the incline, some of that spring potential energy is converted into gravitational potential energy. In other words, the box is going to end up at a higher potential energy. So we've converted some of the initial energy into final potential energy. But also some of that initial potential energy is going to be converted into work done on the box by friction. So this initial energy will overcome the work of friction that will be taking place throughout the travel, and it overcomes this new potential energy. It starts at rest, so it has a kinetic energy at point 1 of 0, and it ends at rest. So it has a potential energy at point 2 of 0. All right, let's move on to a solution. You should notice that we have mixed units here, feet and meters and so on. We should choose one or the other, English engineering system or metric system. I'm going to choose the metric system. So let's convert everything to metric. The mass is already in kilograms, that's good. This spring constant is in pounds per foot, so let's convert 100 pounds per foot to newtons per meter. And it is 3.28 feet in 1 meter. And how many newtons are there in a pound? Let's ask our friend. Convert 1 pound to newtons.
Here's what I found on the web for girlfriend, convert 1 pound to newtons.
Siri thought I said girlfriend, convert 1 pound to newtons. It's 4.45. So 1 pound is 4.45 newtons. Let's see what happens when I cancel units. The pounds cancel, the feet cancel, and I will have an answer of newtons per meter. And if you do this math, you get 1,459.6. newtons per meter. And we had D is 25 feet, so D of 25 feet, 3.28 feet per 1 meter. Feet cancel, and we get 7.62 meters. So that we've looked at the mass, we've looked at the spring coefficient, we've looked at the distance, the angle is good. Spring coefficient is in meters, or the spring distance is in meters. We're all good there. All right, so let's move on now to step 2 of the solution, which will be to use the conservation of energy equation. And in conservation of energy, we have the potential energy at point 1 plus the kinetic energy at point 1 minus the work done by friction equals the potential energy at point 2 plus the kinetic energy at point 2. Now, we've already identified that kinetic energies at start and rest are 0. So we'll go to the next step now, which is to put the equation for potential energy, mgh1, plus there's a spring here, so 1/2 k spring. Let me do that better. There we go. Times the spring compression squared. So potential energy is both gravitational and spring, minus the force or the work of friction. Remember, work is force times distance. So it's force of friction times distance. And that's going to equal potential energy at point 2. Well, at point 2, we're not going to have the spring attached to the box. The spring launches the box up, and the box just travels up. So there is no spring. It's just mgh2. When doing energy problems and finding the heights, we get to say, where is point 0? So let's just decide right now that h1 is 0. So what is h2 then? Let's go ahead and find h2. Well, Well, this is a right triangle that has a hypotenuse of 7.62 meters and an angle of 35 degrees, and this is the opposite leg. So H2 will be 7.62 times the sine of 35, and that is 4.37 meters. Okay, now, let's see, what else do we need to do here? Let's go ahead and do the check mark method. Grab a different